So I'd like to talk to you about major and trace element compositions of chromites from the Stillwater, Bushveld, and Great Dyke, and compare them with chromites from Komatiites, Boninites, and large delayed intrusion provinces. Why do I want to do this? Well, as you're all aware, the three intrusions that contain platinum group element mineralization, the Stillwater, Bushveld, and Great Dyke, their platinum group element mineralization is usually found well into the intrusion, about 2 kilometers in at the JM reef for Stillwater and the Marinsky, and the main sulfide reef at the Great Dyke. However, what we find is that below these sections, we have ultramafic sections which have massive chromite seams. So at the Stillwater, we have about 10 seams labeled A to K. At the Bushveld, we have the lower group chromites, some 1 kilometer into the section, and they're hosted largely by peroxenites and peridiotites. Then we have the upper group chromites, which are particularly interesting because the UG2 is the largest PGE deposit resource in the world. And they are hosted by peroxenites and norites. And then in the case of the Great Dyke, we have 12 massive layers. And in the lower chromites, they are hosted mainly by peridiotites with a bit of peroxenite, but mainly peridiotites. And then the upper section just below the main sulfide reef, we have hosting by peroxenites. So the origin of these layers is not at all clear to us. We have the same sort of problem as we have with the PGEs, in that you'd need a lot of magma to make one of these 1 meter thick massive layers. If you could get every molecule of chrome out of your magma, you'd need 300 meters of magma. And if you want to do things by crystal fractionation and equilibrium, as Cawthorne pointed out a long time ago, you need 3 kilometers of magma or more. So are we crystallizing these chromites and then slumping them to accumulate them? Another model has been that you have hydrous melting of the cumulates. But again, you'd need to melt a minimum of 300 meters of cumulant. So it's not clear at all how these things form. And what I wanted to know, another question is, what is the nature that we're living with? Is it a different magma to the magma that's forming the silicates? So I want to address here the question of, do the composition of the chromites tell us anything about the composition of the magma that the chromites were in equilibrium with? How are we going to do that? Well, there are the currently proposed magmas. There are, for the ultramafic sections, we normally talk about Komatiites that have been contaminated by fractional crystallization for all three intrusions. Although there's also a suggestion that maybe Boninites were involved. And then we perhaps should bear in mind that the Great Dyke and the Bushveld are placed into a cratonic setting. So maybe the Pickrites derived from the lithosphere are important. So how are we going to do it? Well, if you want to look at major elements for chromites, I recommend you go to Steve Barnes's paper in Journal of Petrology. But what I'm going to do now is look at the trace elements in the chromites, because A, we can, now that we have laser abrasion, but B, that gives us a much wider range of elements to think about. And laser ablation, we're going to look at the chromites from Komatiites, and here I'm going to use Alexo because it's in prehnite pampelite facies metamorphism, so we hope it's not too modified in composition. Some Bononites we have, and then the low and high titanium Pickrites from the Emerson province. And then I'm going to compare them with the massive chromatite layers from the three intrusions to avoid any post-cumulus reequilibration. Now, as anybody who's ever done any lasering for the first time knows, you get overwhelmed with data because there's a whole load of elements. And then how can you treat them and think about how they relate to one another? So what I've done here so that I can relate them to one another is I have plotted them in order, first I've calculated the median composition of these trace elements in the Komatiite. Then I've normalized the chromites to the composition of the median chromite from the Komatiite. The idea being here that the chromites from the Komatiites would be the most primitive. And anyway, we want to see if these chromites from the late intrusions crystallize from a Komatiite-like magma. Then to look at the behavior of the different elements, I have plotted them in order of their compatibility with a liquid crystallizing olivine and chromite. Those would be the first two liquids on the liquidus. So from magnesium through to manganese, we're probably looking at olivine control. Chromite is obviously controlling chrome, aluminium, and gallium. And then once pyroxene comes into the picture, we can pick up its activity using scandium. Titanium may give us an indication of how fractionated the liquid is going to be. At copper, I'm not sure what to make of that, but we're having a copper signal, so I just put it there. And then these three elements on the end, we're hoping to look for crustal contribution from hafnium, tin, and indium. And these orange crosses here, that's the detection limit, just a warning that they are very close to detection limit. So these are all of our chromite values from 15 different samples to show you roughly the range you can get from Komatiites. If we look at the Bononite, we see that the Bononite is very depleted in the crustal component, less than detection limit, very negative, strong negative titanium anomaly. It's also depleted in elements such as gallium and aluminium, well below the line for Komatiite here. This is not really a big surprise because Bononites are supposed to have formed by melting of extremely depleted mantle. So naturally the liquid would be depleted and consequently the chromites would be depleted. Turning now to the Pickrites. Here I had to make a scale change to accommodate the higher copper in the Pickrites. We're getting up to 300 ppm copper, which I know some of you are thinking that's just some sort of inclusion, but no, the signals are constant. We've checked it 3 times with different types of settings. I'm wondering if it's something to do with the devolatilization of the magma. Anyway, at the moment, it doesn't matter for our current purposes. So both the low and high titanium Pickrites are enriched in hafnium and titanium, particularly titanium in the high ones. Many of them have negative scandium anomalies indicating the presence of pyroxene crystallization. But overall, their patterns are not that dissimilar to a Komatiite. Now looking at our intrusions. At the Great Dyke, I have samples from the C6 and C8. Those are in the lower part of the intrusion. And what you see here is that they are enriched in hafnium and tin, possibly indicating crustal contamination. Apart from that, the lower chromites, the green and purple line, are similar to Komatiites, although the zinc seems a bit low. Whereas the C1, which is much higher in the intrusion, we see that doesn't seem to be an indication of crustal contamination there, but we see a strong negative scandium anomaly, probably because there's been a bit of pyroxene crystallization. And we're seeing enrichment of gallium and aluminium because probably the magma is more fractionated, and so those two elements have become more enriched. Stillwater chromites, they are very uniform, quite enriched in tin and hafnium, so there seems to be more contamination there going on there. A very strong scandium anomaly, so there's quite a lot of pyroxene crystallization having taken place, even before the first chromite we're looking at, and enriched in gallium and vanadium gallium, probably due to a higher degree of fractionation. The Bushveld is more complicated because there are more layers. So the lower group chromites through to the Mg2, we have some evidence of contamination from hafnium, but doesn't agree. We have strong negative scandium anomalies, probably due to the pyroxene crystallization, and enrichment in gallium and a bit of vanadium. Otherwise at about Komatiite levels. From the upper group chromites and from the Mg3, and here I've included the data also from the northern limb that Langler recently published, and those are shown as these are the orange ones here. We see a more enrichment of hafnium and tin, possibly more contamination. We see that there's more titanium and higher vanadium and gallium, so it's probably more crystallization. You can also note that the northern limb UG is poorer in scandium, chrome, and nickel. So, what do we know so far? The negative scandium anomalies and high incompatible chromites show that we cannot crystallize these Komatiites directly from a Komatite or a Bononite for that matter. What I decided to try and do here was look and see what we could do with the chill rocks. Now, here we have a plot of chrome versus aluminium, and I used melts to plot the crystallization trends if we had the acicular pyroxenite chill. So that's the most magnesium-rich chills we see at about 20% magnesium. We found a couple at Great Dyke and at the Bushveld. And that's the black line here. So that's what happens as you crystallize those. And at some point, plagioclase comes in and aluminium goes down. And along most of this line, at first you're just crystallizing olivine, but for much of the line, you're crystallizing olivine and pyroxene, orthopyroxene in particular. What we see is the Great Dyke samples, and here I've added Alan Wilson's massive chromatites to our own data set. We see the lowest ones are the least crystallizing from the least fractionated chill, but we could make the chromites from the acicular pyroxenitic chill, which has about 15% crustal contamination of a Komatiite. For the Stillwater, we can see a few of them would be satisfied with this chill, but mostly the Stillwater samples are lower in chrome and a bit richer in aluminium. So we really need to go for the B1 chill of the Bushveld, which has more crustal contamination. And we could probably satisfy the Stillwater samples. If we, and I just showed the position of the Komatiite and the low titanium Pickrites on this line. If we look at the Bushveld now, that's a bit more complicated again. We have the line for the acicular pyroxenite chill, and maybe a few of the lower group 1 to 2 could be satisfied with,
warning.
Okay, with second last slide. Maybe they would be satisfied. But when we get to the LG5 and going into the MG and upper chromites, we see that we have too much aluminium, and we'd have to use either the B1 chill or possibly a mixture of the B1 and B2 seems a little bit more satisfactory. Interestingly, and I don't know why, but when we look at the UG2 from the northern limb, it seems to be more fractionated and is obviously crystallizing plagioclase. That's just all of them together. Okay, so all of the chromites contain too much titanium, aluminium, hafnium, be in equilibrium with the Bononite. Trace elements are similar to Komatiite chromites, or low titanium pickrites, except for the negative scandium and some hafnium tin enrichment. Great Dyke have the highest chrome, and wood and the lower group chromites of the Bushveld could be satisfied by the secular pyroxene chill. UG2 would fall along this, if in the north, would fall along the same line, but appears to have crystallized with plagioclares. The Stillwater chromites and the LG5 to LG3 are too aluminium rich for the acicular pyroxenite and form more along a B1 or B1, B2 mixture. Thank you.